Thank you for having me today. I'm really excited to be up here to be in front of this mixture of aviation leaders to talk about something that's really important to me, but to also highlight what state-level investment in infrastructure is doing to further aviation growth. In fact, this picture up here is actually a state-owned asset deployed at Burns Flat, which I'm going to highlight a little bit later. But today specifically, I want to talk about scalable autonomous operations in mixed-use, low-altitude airspace. As you now feel, it's 9 to 10 a.m. But the engineer in me wants to really bring forward this conversation that scalable infrastructure is a pathway to commercially viable beyond visual line of sight operations. For a long time, the attention of autonomous aviation has been on the aircraft, the drones, the battery, really the automation of the payload, and that makes sense. The aircraft really has matured. But increasingly, the question is not, can the aircraft fly? That much is obvious. The question now is a little bit more precise. Can the systems operate safely, repeatedly, and at scale inside the National Airspace System? And that is a different challenge. It requires us to not only think about the aircraft capability, but also the infrastructure layer that allows these aircraft to operate safely in shared airspace. And so I can anchor one thing for my whole talk here is that safe autonomy requires scalable infrastructure. Commercial BVLOS. This is why the timing matters for the state's investment in this types of systems, especially Act Kendyn 1. Part 108 helps move beyond visual line of sight from individual approvals towards a more repeatable commercial operation. This is important because the opportunity is clearly commercial. We can all imagine the applications: package delivery, agriculture operations, infrastructure inspection, emergency response, medical logistics, the list goes on. But basically, anything where the aircraft is more valuable beyond visual line of sight and not constrained to visual observers. The scaling challenge is operational evidence. In other words, regulatory process opens the door, but to walk through that door at commercial scale, operators will have to show that their operations are conducted safely and repeatedly. That means showing what was in the airspace, what was detected, how the system performed, and whether the risk was managed appropriately. So the opportunity is commercial, but the pathway has to run through safety evidence. And this is the core shift. Autonomous aviation does not scale by eliminating risk. And that's kind of an odd saying, but really, no aviation system eliminates risk entirely. Aviation scales by identifying, measuring, mitigating risk, and showing that the residual risk is acceptable for the operation being conducted. And that's what we care about in shared mixed-use airspace. And this is especially true for beyond visual line of sight. The new challenge is managing operational risk at scale. Risk mitigation requires safety evidence. Proving the safety case requires infrastructure, and infrastructure enables data collection at scale. A single successful demonstration is very valuable to show that a new aircraft works, but it's not the same as proving that it's repeatable, safe operations in shared airspace. Commercial beyond visual line of sight requires stringent evidence across repeated flights, real environments, changing conditions, and shared airspace. And that's where the infrastructure becomes essential. Historically, aviation has depended heavily on human observation, pilots seeing and avoiding, drone operators maintaining visual line of sight, visual observers extending that awareness. That model works for limited operations, but increasingly it's not going to work any longer. The human eye does not scale to dense, mixed-use, low-altitude operations across larger areas. At scale, autonomy is fundamentally an observability problem. Operators need awareness beyond what one pilot or one observer can physically see. They need awareness of cooperative aircraft, non-cooperative aircraft, drones, terrain, operational boundary, and even changing conditions. So the question now becomes, how do we move from human visibility to persistent airspace awareness? And this is where electronic observation comes in. Seeing is limited. It depends on where a person is standing, what direction they're looking, what the weather is doing, and even how far away the aircraft is from the observer. Observation in this context means something broader. It means that infrastructure-enabled ability to detect, track, fuse, display, and record what is actually happening in the airspace in real time. Electronic observation is a scalable pathway because it doesn't rely on simply just adding more people to your operations to make it safe. It allows us to move from a standalone observer model towards network sensors, integrated data, and eventually broader shared awareness across larger systems. We're not saying that the human goal will disappear entirely, but really that the human goal has to be supported by infrastructure that observes the airspace consistently and more broadly than the human eye alone. And currently on this roadmap, we're pretty much over here on the left, where we're employing electronic observation to increase situational awareness. But the future could look like this: UTM, autonomous systems at scale, shared infrastructure. That's the pathway that we set ourselves on with some of the investment that the state is currently doing to further grow the aviation industry. And this brings me to what matters most. This is where the Oklahoma story matters. Oklahoma is investing in an infrastructure layer needed to support scalable autonomous operations. The goal is not just to install sensors, it's actually to generate operational evidence for the safety case. And that distinction matters. The sensor by itself is really just a piece of equipment. The infrastructure is what happens when those sensors are placed, networked, modeled, integrated, and then used to support real operations. At Infinity One Spaceport in Burnside, Oklahoma, the work is actually about building an environment where low-altitude airspace can be observed, measured, and understood, specifically quantified for safety. And this is important for operators, regulators, and communities. And it's also important for Oklahoma's ability to support the next stage of aviation growth. This map here shows some theoretical placements of where we would be planning to put S-200 radars and their approximate detection range. And I'll get into a little bit later that detection range from the manufacturer isn't always what the sensor can see, and that's some of what the work is actually related to, deploying these sensors in the field. And there's a practical layer to all this. Infrastructure enables electronic observation. On one side here, you have a fielded, this is a fielded radar, a 3D-7360. It's a huge advancement in radar technology to where, unlike traditional radar systems, where we see something in your plane and say, oh, it's over there, this can say, hey, it's over there, and it's also this high up in the air. That gives rapid situational awareness in relation to where your aircraft is versus where another aircraft is in time and space. On the other side here, this is the common operating picture. This is what my company specializes in. This is Flight Horizon, our company's flagship system that's actually deployed at Infinity One, integrating radar data, ADS-B, telemetry, drone alerting, airspace boundaries, and also, most importantly for the regulators, it records what happens in the airspace. The value of these systems is not just what it sees, but also that it turns multiple sources of data into usable operating picture, specifically to support safe operations, the decision layer, what the pilot is actually doing in real time. And it's also important because, like I said, it creates a safety record. Because when we talk about scaling beyond visual line of sight, we are not only talking about real-time awareness, we're also talking about what can be shown after the operation, the safety artifacts. What happened? What was detected? How early was it detected? How did the system perform? That record is part of the safety case and probably one of the most important artifacts. This slide brings the concept into real-world deployment. Flight Horizon Tempo integrates radar, ADS-B, drone telemetry, and it creates a common operating picture. It's deployed at the Infinity One Spaceport in Burnside, Oklahoma, where the primary goal is to replace visual observers with electronic observation and to prove the safety case to the FAA that integrating drones into national airspace is viable, specifically enabled by infrastructure. This matters because commercial viability depends on repeatability. If a company wants to operate beyond visual line of sight at scale, they need to have more than just confidence that the aircraft can complete a flight safely. It needs evidence that the system can detect all relevant traffic, to include non-cooperative traffic that are not broadcasting their location, or drones that are not compliant with the RID rule. It needs evidence that the system can detect, that operators can maintain awareness, and that the operation can be repeated under real-time conditions. This is a bridge from demonstration to commercial operation, and it's why operational evidence supports the commercial viability, and Oklahoma is already ahead of the curve by deploying these systems to start proving that safety case on what integrating drones in the airspace could look like. But there is ongoing work. It's not enough to fly a radar. You have to, what I like to call, engineer observability. This is a very technical diagram. The nerd in me kind of wants to deep dive and explain it. I'll keep it high level here. Basically, observability has to be engineered. Radar placement matters, the sensor itself matters, terrain matters, modeling the airspace accurately to what the sensors see matters. This picture on the slide is good proof that you can get pretty good approximation of what the radar will see, but in real world deployments, if there's a hill on the bottom right here, you may not see your drone when it goes over that hill. And so that's some of the work required deploying these sensors to clutter map them and understand what they see. It's important when the goal is repeatable beyond visual line of sight, because if we want to rely on electronic observation, we need to understand the performance of that observation. And more charts that I can nerd out about. But basically, this brings me to the next step and the ultimate goal of this deployment, is that we need to turn all of this awareness, all of this observation into repeatable safety artifacts that can show the FAA that we're doing something that is safe, that we're mitigating risk, and that we are collecting data not for data's sake, but to use as safety evidence. This includes flight activity, sensor performance, coverage results, detection history, and even operational records. Over time, that information will help answer the questions that matter for the safety case. What was in the airspace? What was detected? Where was the coverage strong? Where was the limitations? How did the system perform across repeated operations? It helps produce the evidence needed to improve operations as a whole, support approvals, and also inform procedures and build confidence in commercial BVLOS. This right here is actually called a view shed, and what you're looking at right here is a theoretical view of what the radar can and cannot see. The green over here shows that the radar can see these areas. The areas not colored in green show that there's some terrain there where the radar may not be able to see. And so when we deploy these systems, we need to take into account the geometry of the radar and what's actually happening out there. And this leads me to the full system view. Aircraft capability is very necessary. Having a drone that can even do a beyond visual line of sight because of its battery, because of its rotors, that's all great. But aircraft capability alone does not create scalable autonomy. The next layer is obviously airspace observability, and that's where Oklahoma is actually putting these systems in place to start proving that case. From observability, we get operational evidence, and from operational evidence, we can support scalable autonomy. And that's really the main point of my talk, is that infrastructure is what connects aircraft capability to scalable autonomy. Without the infrastructure layer, we may have capable aircraft, but we don't yet have a full system that will support the safety case for operations in shared airspace. Autonomous aviation is not just an aircraft problem, it's an airspace integration problem that's enabled by infrastructure layer. And that's what Oklahoma is doing today, that's what my company is working on. Questions? Thank you.